Picture a clear night sky, the kind of night where the air is crisp and the stars seem to be within arm's reach. Thousands of stars twinkle above, each a distant sun in the vast expanse of the Milky Way. These stars, some of which have been shining for billions of years, create a mesmerizing spectacle that has captivated humanity since the dawn of time. This cosmic tapestry has adorned the night for millennia, a source of wonder and inspiration. Poets, philosophers, and scientists alike have gazed upon this celestial canvas, pondering the mysteries of the universe. But what if, one day, a star simply vanished? No fiery explosion, no fading light, just a sudden disappearance, as if it had been plucked from the sky by an unseen hand. Just an empty patch where once a star burned bright. This eerie absence would be more than just a missing point of light. It would be a profound reminder of the dynamic and ever-changing nature of the cosmos. This, my friends, is the unsettling possibility when a black hole is born. Black holes are the remnants of massive stars that have ended their life cycles in spectacular fashion, collapsing under their own gravity to form regions of space where the gravitational pull is so strong that not even light can escape. These celestial objects are shrouded in mystery and often misunderstood. They are not just voids in space, but are incredibly dense points where the laws of physics as we know them break down. Black holes are not cosmic vacuum cleaners, relentlessly devouring everything in their path. In fact, many black holes coexist peacefully with their stellar neighbors, exerting their influence only on objects that venture too close. Instead, they are fascinating objects that challenge our understanding of gravity and the very fabric of space-time. The intense gravitational field of a black hole can warp space-time itself, creating phenomena such as gravitational lensing, where light from distant stars is bent around the black hole, creating a distorted yet beautiful view of the universe. They are reminders of the immense power and beauty of the universe we inhabit. Black holes, with their enigmatic presence, push the boundaries of our knowledge and inspire us to explore the cosmos further, seeking answers to the profound questions about the nature of reality and our place within it. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where matter has been compressed into an infinitely small point. This point is called a singularity. Around the singularity lies an invisible boundary called the event horizon. Once something crosses the event horizon, there is no turning back. It is forever trapped within the black hole's gravitational grasp. The very laws of physics, as we understand them, break down at the singularity. This makes black holes one of the most intriguing and perplexing phenomena in the cosmos. Black holes can vary in size, from stellar mass black holes formed by collapsing stars to supermassive black holes found at the centers of galaxies. They can merge, creating powerful gravitational waves that ripple through space-time. Some theories suggest black holes can emit radiation, known as Hawking radiation, slowly losing mass over time. Their immense gravitational pull can influence nearby stars and gas, often forming an accretion disk, and sometimes even emitting powerful jets. Understanding black holes helps us unlock the mysteries of the universe, from the behavior of matter under extreme conditions to the evolution of galaxies. Black holes come in a variety of sizes and types. The most common type is the stellar mass black hole. These form when a massive star exhausts its nuclear fuel and collapses under its own gravity, often following a spectacular supernova explosion. Stellar mass black holes typically have a mass ranging from about 3 to several tens of times that of our Sun, yet they are compressed into a region no larger than a small city. At the other end of the spectrum, we have supermassive black holes. These colossal giants reside at the centers of most galaxies, including our Milky Way, and possess masses that are millions to billions of times greater than that of our Sun. There are also intermediate mass black holes, which are thought to form through the merging of smaller black holes and can be found in star clusters. Lastly, there are hypothetical primordial black holes, which might have formed in the early universe due to high-density fluctuations shortly after the Big Bang. Each type of black hole plays a unique role in the cosmos, shaping the structure and evolution of galaxies and influencing the dynamics of the universe. At the heart of our Milky Way galaxy, approximately 26,000 light-years away, lies a sleeping giant. Sagittarius A is not just any ordinary celestial object. It is a supermassive black hole, a cosmic entity with gravitational forces so strong that not even light can escape its grasp. This supermassive black hole, with a mass of about 4 million suns, governs the motions of stars in its vicinity. The stars near Sagittarius A * move in intricate and rapid orbits, influenced by its immense gravitational pull. These stellar movements provide crucial insights into the nature and behavior of black holes, helping scientists understand the dynamics of our galaxy's core. While it may seem intimidating, Sagittarius A is in a dormant state. This means it is not currently feeding on a significant amount of material, making it appear calm and subdued. It's not actively feeding on a large amount of material, so its influence on our solar system is negligible. The lack of a substantial accretion disk, which is a disk of gas and dust spiraling into the black hole, indicates that Sagittarius A* is not in an active phase of growth. This dormancy provides a unique opportunity for scientists to study a supermassive black hole in a relatively quiescent state. However, its presence reminds us that even in the seemingly tranquil expanse of space, colossal forces are at play. The existence of Sagittarius A* serves as a powerful reminder of the dynamic and ever-changing nature of our universe. It highlights the delicate balance between calm and chaos, and the incredible forces that shape the cosmos. As we continue to explore and learn more about this enigmatic giant, we gain a deeper appreciation for the complexities and wonders of our galactic home. Recent studies have revealed that Sagittarius A* occasionally emits flares of X-ray and infrared radiation, suggesting sporadic feeding events. These flares provide valuable data, allowing astronomers to probe the environment around the black hole and understand the mechanisms driving these outbursts. Advanced telescopes like the Event Horizon Telescope have even captured the shadow of Sagittarius A*, offering a glimpse into the event horizon, the boundary beyond which nothing can escape. This groundbreaking observation has opened new avenues for testing Einstein's theory of general relativity under extreme conditions. Additionally, the magnetic fields around Sagittarius A* play a crucial role in shaping its behavior. These fields can influence the formation of jets, streams of particles ejected at nearly the speed of light. Understanding these magnetic interactions helps scientists piece together the complex puzzle of black hole physics. As we delve deeper into the mysteries of Sagittarius A*, we uncover the profound impact it has on our galaxy. From governing stellar orbits to influencing galactic evolution, this supermassive black hole is a key player in the cosmic drama unfolding in the heart of the Milky Way. Black holes are among the most enigmatic and awe-inspiring phenomena in the cosmos. They are regions where gravity is so overpowering that nothing, not even light, can escape their grasp. The most dramatic way black holes come into existence is through the cataclysmic death of massive stars. These colossal giants, far larger than our sun, live fast and burn bright, consuming their nuclear fuel at a breakneck pace. Stars are the universe's nuclear reactors, perpetually fusing hydrogen into helium in their cores. This fusion process is the powerhouse that fuels the star, producing the radiant light and searing heat we observe. This relentless fusion releases the energy that makes stars shine brilliantly. The delicate balance between the outward pressure from fusion and the inward pull of gravity maintains the star's stability for most of its life. But this equilibrium is not eternal. As the star ages, it begins to deplete its hydrogen fuel. Eventually, the star exhausts its nuclear reserves. With hydrogen gone, it starts fusing heavier elements like helium, carbon, and oxygen. At this critical juncture, the outward pressure from fusion can no longer counterbalance the relentless inward pull of gravity. The star's core becomes unstable and succumbs to a catastrophic collapse under its own immense weight. The core implodes, compressing matter to an unfathomable density. This cataclysmic event unfolds in mere seconds, a blink in cosmic time. This implosion ignites a supernova explosion, hurling the star's outer layers into the void. The explosion is one of the universe's most spectacular displays, momentarily outshining entire galaxies. What remains is a black hole. The collapsed core transforms into a singularity, a point of infinite density encased by an event horizon, the boundary beyond which nothing can escape. This is the dramatic birth of a black hole, a cosmic abyss that continues to captivate and baffle scientists and astronomers alike.